Today we're integrating with respect to time. Now we've already seen that when we differentiate displacement we get velocity, and when we differentiate velocity we get acceleration, but it also makes sense that we can go back the other way by integrating, and that's what we're doing today. Now when we integrate we always get a constant of integration. That's our plus c on the end, the unknown. And to find that c we need a clue. Now when we're dealing with motion and rates, we can get in all types of clues. They might say when time was 4, velocity was this, or whatever. But often what we'll get is something we call the initial condition. So look out for that because it's really common. Now initial means at the start. So the conditions at the start would tell us that when time was 0, x might have been a certain value, or v might have been a certain value. Now if we're going from acceleration to velocity, we'll need to know a clue for velocity to find out that velocity formula. And if we're going from velocity to displacement, we'll need a clue that involves x. And if we're going both steps, we'll need a double clue, or 2 clues in one. And here's an example. A particle is moving with this formula for v. Now v is velocity. So it's moving at 2t minus 2 meters per second, where remember we're thinking of t as time in seconds. Initially, it is at x equals 1. Now that's our clue that we're going to need to use to find the integration constant. So we've got a bunch of questions here. Let's work through them one at a time. A, find the displacement formula. Well, if we have v and we want to find x, which is the displacement formula, that means we need to go up a step. If you think of the displacement, velocity and acceleration as moving down in some sort of a hierarchy, then to go back up we need to integrate. So integrating 2t minus 2 with respect to the t, I can integrate this term and get t squared. Remember, every time you integrate, just differentiate your term to check to get back to the one that you're given, minus 2t plus c. Now to find our constant of integration, we need to use our clue. Now initially that means t equals 0, x was equal to 1. So I'll write down what I'm doing here. I'm going to sub in t equals 0, x equals 1, and see what I get for c. So I've got 1 is equal to 0 squared minus 2 lots of 0 plus c. So these parts equal 0, so c equals 1. Now I can write my formula out. Knowing what c is, I've got my t squared, I've got my minus 2t, but now instead of leaving that unknown on the end, I know that I have plus 1. Now if I'm graphing this or using it for something else later, it might be handy to look at all of its disguises. It's perfectly okay as it is, but if I can see that I can factorize it, then it's smart to go ahead and do so, because it might help me later on. Certainly it will help me to graph it. I can see straight away where the intercepts would be, and that will give me a lot of information. B, when is the particle? Now underline the important parts. When. So we need to know the t value here. When is the particle at the origin? And what is the velocity then? Okay, the first thing to do is to find when the particle is at the origin. Now the origin is the point x equals 0. So for B, I need to sub in, let x equal 0, and solve for t. Now I can use either version of these formulas here, but see how straight away this factorised one makes my life easy. If I've got 0 equal to this, then obviously t has to be 1. Now bear in mind that in our course time is always positive too, so if you get some answer where you've got a positive and a negative version of time, go for the positive one. So therefore at time t equals 1, or in other words after 1 second. Now when is the particle at the origin? Okay, it's at the origin after 1 second, or you could write that. What is the velocity then? Okay, well we need to now sub in when t equals 1, velocity equals, and we were given the velocity all the way back up in the question. All we've got to do is now put in 1 for t. So we've got 2 lots of 1 minus 2, and that's just 0. Now why have I gone to the lengths of subbing all of this in? Well, questions like these involve lots of working and it can get a little bit confused. So if you've been asked a question, it's good to really show the examiner you know what you're doing. Instead of just writing when t equals 1, v equals 0, I've written this out so it's really obvious that I've subbed it into this. I've done 2 lots of 1 and then I've subtracted 2. Also just prevents you from making a mistake. So to answer the question, when is the particle at the origin? It's after 1 second. So therefore, after 1 second, x equals 0, and the velocity is also 0. Now, we should probably put units. 0 meters, velocity is 0 meters per second, because we have these units up here in our question. C, explain why the particle never travels left of the origin. Well, looking at where the particle is, that's displacement. So let's look at our displacement formula. Again, this one is helping us. Displacement equals the time, take off 1 second and then square it. Well, anything that's been squared is always positive. This explains to me why x is always going to be a positive number. So we must be always on the right-hand side of our number line if this is a particle moving along a number line. So I would just write anything squared is positive. And we know that x equals t minus 1 all squared. That's a good explanation, I think. D, find acceleration and show that it is constant. All right, we were given velocity. That means if we want to find displacement, we go up one level by integrating. But if we want to find acceleration, we need to differentiate to get to the next of those things in our hierarchy. So differentiating this is very simple. Differentiating with respect to t, we just get 2. So acceleration equals 2, since, now I'm just going to explain why, acceleration is dv dt, which is 2. And show that it is constant. So it definitely is constant because it's 2 and it doesn't have any variables in it. Now in that last question we weren't asked to graph displacement, velocity or acceleration, and it was quite easy to answer all of those questions without really imagining what the particle was doing or playing it out in our heads. But in case we want to do that because the question asks us to, or because we're just interested in understanding what's happening with these equations, the equations from that question would look like this when graphed. Now, I've just used my graphing skills here to graph a parabola. This is a basic parabola that's just been moved to the right 1 step. And this is a straight line with a gradient of 2 and a vertical intercept of -2. And this is a horizontal line going across at a equals 2. So they're quite simple to graph. What's happening then to this particle? Well, it's obviously moving along the number line. It's not moving in 2 or 3 dimensions. It's literally going along the number line. So if I just imagined a number line, we said that it was never going to the left of the origin. It was actually only moving along like this, on this side. Well, let's act out that movement based on these graphs so that the graphs make more sense and the equations themselves make more sense. It started at 1 on the number line, and then after a second, it was back down at the origin because this stands for 0. So it started here, it went down there, and then obviously it must have turned around because it went up again to 1 on the number line, 2 on the number line, 3, etc., and kept going. So it went down there and then up here and kept on going in this direction. The graph of the velocity backs this up because it says the velocity was actually 0. This is 0 velocity here after 1 second, which makes sense because it must have turned around at that point. So for just a moment, it was still. Then it continued to go up. Now see here how the velocity is constantly increasing? That's because in the beginning it was negative and then it turned positive. And that graph shows you that negative velocity in the beginning because the particle was going backwards. The acceleration is constantly 2, okay? Now if you look at that, it's easy to imagine that it's always just speeding up right from the beginning, and you may not have envisaged this starting at 1 and going backwards, turning around and going again. But that's exactly what these formulas show must have happened.